The last topic we're going to talk about trigonometry is dealing with a little bit of vector problems. We're not going to go into exactly what they are, we're just going to do the trigonometric side. Okay. In what follows, we're going to be talking about triangles that are not usually right triangles, because let's be honest, most triangles are not right triangles. Now, because we don't want to draw the picture every time, and we don't want to have to explain it every time, anytime we're doing problems like this, if they say the angles are capital A, B, and C, then the sides are known for us. Angle capital A, the side opposite is angle lowercase a. Angle capital B, the side opposite is angle lowercase b. Side capital C, the side opposite is side lowercase c. So sides and angles are always named the same, just opposite each other. Now, we have two new theorems, okay? They're kind of taking place of the definition of sine and the Pythagorean theorem. Only both of those require the triangle to be a right triangle. So these two theorems do not require a right triangle. First, we have the law of sines. Which is that if I take the ratio of a side divided by the sine of the angle opposite it, it's the same for a triangle no matter which side I chose. Now there is a very serious warning attached to the law of sines. When you're using, so usually what happens is you pick two of these, plug in three of the four quantities and solve for the fourth. Okay? When you're using law of sines to find an angle, we will eventually have to take a sine inverse to get to the angle. And this is where the problem comes in. Sine inverse lands in quadrants 1 and 4. Now, no triangle has an angle in quadrant 4 because they're too big for a triangle. But there are triangles with angles in quadrant 2, obtuse triangles. But sine inverse never lands in quadrant 2, which means that if you have this little trouble, if you're trying to find an angle using sine inverse, you don't know if you're actually in quadrant 1 or quadrant 2. There can be some ambiguity. We'll cover ways to deal with that to hopefully avoid it. The next one is the law of cosines. There's actually three versions of this. You'll notice that all I'm really doing from here to here is I changed all the places of the B's and C's. And from here to here, I'm changing the C's and the A's. You'll also notice that this first one, when capital C is a 90-degree angle, the cosine of 90 degrees is 0, so this term disappears and it turns into the Pythagorean theorem. So this is actually a generalization of the Pythagorean theorem that holds for any triangle. Okay? Now, we're also going to be talking about real-world problems here. So we have two different ways of measuring direction in the real world that we're going to cover. The first is heading. Okay? Heading is always an angle measured clockwise from north. So it'll be an angle between 0 and 360, and you just start at north and continue clockwise until you hit your angle. I don't like this one because of the clockwise little issue there, because the rest of trigonometry we do counterclockwise. So I am more likely to use a bearing. Okay. What a bearing is an acute angle, meaning an angle between 0 and 90 degrees, formed by the north-south line and the line of direction. So this one is a little bit more confusing to begin with, so I have two examples over here. First of all, this is illustrating a bearing. We have the north-south line, the angle of direction, and we have the acute angle between them. If I want to write this, I would start with either north or south. In this case, I'm measuring from north. So I start at north, and I go 78 degrees east from there. So this is north 78 east, because again, I started at north and went 78 degrees towards east. To make sure we can go the other direction, let's turn this angle into the picture. I'm going to start at south, and I'm going to go 65 degrees towards west. It's just going to be over here, and the 65 degrees will be down here.